System architecture. The performance of an EAEC system is strongly influenced by the design of the heat exchanger and the configuration of airflow paths. Plate heat exchangers are the most widely used solution, offering a compact and reliable means of transferring heat between adjacent airstreams. In contrast, closed-loop runaround coil systems decouple supply and exhaust AHUs entirely, enabling separate plant rooms, retrofit installations, and integration with additional hydraulic components such as heat pumps. Capabilities are not achievable with plate exchangers. Cross-flow arrangements are common in packaged air handling units owing to their simplicity and ease of manufacture, although counterflow configurations can achieve higher effectiveness where geometry permits. In both cases, the exchanger typically incorporates alternating dry and wet channels, with the exhaust air passing through wetted passages and the supply air through dry ones. The effectiveness of heat transfer depends on factors including surface area, airflow velocity, and the uniformity of water distribution on the wet side. Where physical separation of supply and exhaust ducts is required, runaround coil systems, which are effectively a counterflow heat exchanger, provide an alternative. These systems use a pumped liquid loop, typically water with glycol, to transfer heat between coils located in separate airstreams. While the dual heat transfer step introduces additional thermal resistance, modern runaround coil systems with optimized coil geometry, low approach design, and variable speed circulation pumps routinely achieve sensible recovery efficiencies of 65 to 75%, narrowing the gap to plate heat exchangers significantly. In return, they offer considerable flexibility in layout and eliminate any risk of cross-contamination. This makes them particularly suitable for applications such as healthcare and laboratory environments. If adiabatic cooling is insufficient, it is possible to add additional cooling to the circuit via a plate heat exchanger. This can eliminate the need for conventional cooling coil in the supply air, which can reduce the airside pressure loss and result in more compact air handling unit, AHU. In practice, the cooling capacity of an EAEC system is constrained by airflow rates and heat exchanger effectiveness, and it is rarely sufficient to meet peak loads in isolation. Consequently, it is most commonly deployed as part of a hybrid system, acting as a primary pre-cooling stage ahead of conventional mechanical cooling. By reducing the temperature of incoming air before it reaches the cooling coil, the system lowers the sensible load on the chiller, enabling smaller plant sizes and improved part load efficiency. In many cases, this top-up approach allows the vapor compression system to operate only during peak conditions, significantly reducing annual energy consumption. In systems where a runaround coil is installed, additional cooling can be provided in summer and supplementary heating in winter through an integrated heat pump. This uses the exhaust air as a low-grade heat source in winter, which can be used to preheat the incoming supply air and as a heat sink in summer. This approach increases year-round efficiency by enabling the system to operate in both summer and winter. The single hydraulic loop can simultaneously provide sensible heat recovery, adiabatic cooling support, heat pump integration, and trim heating cooling, consolidating functions that would otherwise require multiple separate components in a plate heat exchanger based AHU.